Swayam Prabha. Digital India. Educated India.
So, you see there are two factors, one is environment, another one is distance. These two factors we have discussed. Now, let us get into another important factor which guides galvanic corrosion, that is area factor. So, area factor is one of the most important issues in galvanic corrosion, and we have already cited three examples. One is Monel hull and steel rivet, or copper plate and steel rivet, or a tank with a bottom of the tank is made of stainless steel, 1880 stainless steel, and the joint part, which is the joint part between the mild steel and stainless steel, that section will be very vulnerable to galvanic attack because of this differential area effect. So, why area effect is important? When we discussed about the mixed potential theory, we have seen that if zinc is coupled with platinum, and if zinc and platinum couple is placed in acid solution, then we see that if the area of zinc and platinum they are same, then the corrosion rate, let us say if corrosion rate is C1, and if we have a platinum area which is more than the zinc area, then the corrosion rate of zinc will of course will enhance. Now, the point is here on the platinum surface we have cathodic reaction, which is hydrogen evolution since it is acid solution, but on zinc surface it is a zinc dissolution. And let us again see that particular diagram, that is when we consider mixed potential theory, which is E versus log capital O. Please remember this is not current density, this is rather total current. Now, that time if we plot mixed potential theory, we will see that if zinc and platinum they have the same area. Now, this is basically I0 or I0 hydrogen on zinc surface, and this is I0 zinc plus plus on zinc surface, this point, and this is let us say irreversible of zinc, this is irreversible hydrogen. Then we have on zinc surface one cathodic reaction, which is hydrogen evolution, another cathodic reaction which is actually the same cathodic reaction, which is hydrogen evolution, which is happening on platinum surface. And we all know that on the platinum surface hydrogen exchange current density would be much higher than the exchange current density of hydrogen on zinc surface. So, this is hydrogen exchange current density on platinum surface, and if it is the same area, let us say 1:1, area ratio is 1:1, then we have corrosion current density. This is my I core, and the dotted line actually indicates that this dotted line combines the hydrogen evolution reaction current density on platinum and hydrogen evolution reaction rate on zinc. Both these rates are combined on this dotted line. Now, if we increase the platinum area, let us say initially it was same area ratio, this is platinum, this is zinc, 1:1 area ratio. Now, if we increase this platinum area by 3-fold or 5-fold, then platinum, this is let us say this is 1:3, the area ratio would become 1:3. Then the total number of hydrogen reaction on the platinum surface would increase. Now, if the total number of hydrogen reaction on platinum surface increases, then the total current would increase. Current density, exchange current density would not change, but the total current density, total current would increase on the platinum surface for the hydrogen reaction. Now, instead of I0, since this is on the scale of current, we can also indicate as capital I0 for hydrogen evolution on platinum surface. This is capital I0 of hydrogen evolution reaction, exchange current, rather exchange current density, we use exchange current of hydrogen on zinc surface. So, if we see that the number of reactions are increasing on the platinum surface, though the exchange current density will not change, but the total current density, total current corresponding to the exchange rate of hydrogen evolution reaction on this higher platinum area would increase. So, that time this would be my I0 dashed hydrogen evolution on platinum. This indicates the exchange current on the platinum surface. If we increase the area, then I will see that the rate would increase. Now, the situation is the current density is here, and this dotted line combines this, the reaction rate of hydrogen on this reaction on platinum surface with higher area, and this line. So, this dotted line indicates combination of this, and this line indicates the combination of this and this. So, now we see that the total current or the total current corresponding to the corrosion point increases with respect to this. So, if we increase the area of the cathodic part, we see that the corrosion rate on the zinc part would increase. Why? The same current will be felt by the small area zinc. So, if we increase the current, total current on the small area of zinc, then my current density corresponding to the corrosion rate, which is proportional to the corrosion rate on zinc surface, would be then this I core divided by small area zinc. Now, if it is small area zinc, then the current density at this point for zinc would be much higher compared to the current density of zinc dissolution on zinc at this point. This is much higher than this. So, the corrosion rate of zinc would increase if we increase the cathodic area. So, this is the area effect. Now, the same thing would be true if we have copper plate. This is the 2 copper plate. Now, if we, this is these 2 copper plates are fastened with steel rivet. This is the steel rivet, this is my iron. Steel is nothing but iron. So, the iron rivet is fastening copper plate. Now, the same situation will prevail there. Now, here what is cathode here? Let us say this entire stuff is put it in sea water. Now, in this situation, we go to galvanic series, and in the galvanic series copper is noble and iron is active. Since copper is above iron in the galvanic series in seawater solution. So, copper will act as cathode. So, what would be my cathodic reaction in seawater? The possible cathodic reaction is this is my cathodic reaction, and if this is my cathodic reaction, so the anodic reaction would be, since iron is active here, so iron will dissolve. This is my anodic reaction. Now, if the, and here we see that the copper area is much higher than the anodic area, or the cathodic area is much higher than the anodic area. So, the same situation will prevail. What would happen? The rate at which the iron will dissolve will be much higher, since the area of the cathodic part is much higher compared to the area of the anodic part. So, in this situation, the dissolution of this steel rivet will happen very quickly, and this entire stuff will become very loose. Now, how to? So, we see one particular phenomena, that if area of cathode is greater than area of anode in a particular solution, that situation is very bad. Then that time the anodic dissolution would be much faster compared to the situation where area of cathode and area of anode both are same. Now, the favorable situation where my control would be better on the corrosion rate, area of the anode if it is less than the, if it is more than the area of cathode. So, this is one important observation. Another observation is small area of anode and large small area of cathode and large area of anode. This is unfavorable and this is favorable. Now, let us say I reverse the material. If this is my copper rivet and this is my steel, the plates become steel and the rivet become copper, that time situation would be much better. Why? Still in the sea water, iron will act as anode, copper will act as cathode, but the area of the anode is much higher compared to the area of the cathode. So, the number of anodic reaction would be less, since the area available for cathodic reaction is less, and consequently the consequence would be the corrosion of the iron plate would be much slower. Still the corrosion of iron plate would occur, but at a much slower rate compared to the situation where we have this. So, the main point is we have to have a situation where the area of the cathode should not be more than the area of the anode. This is one situation. The same happens if we have the Monel hull with a steel rivet. There also the hull strength would decrease because there would be aggravated corrosion on the steel rivet because of this unfavorable area factor. Now, we have one more classical example. Let us discuss that part. Let us say we have a water tank. This is my water tank. And the roof is also made of steel, and this is mild steel. This is mild steel water tank, and let us say we have water which is industrial water, and that is, let us say, mildly corrosive to the system. Now, this tank can operate for a very long period, even maybe more than 10 years or so. and there would be definitely some corrosion effect, because there is dirt, there are dirts in the solution and all other effect. And more importantly, generally if we put a phenolic coating on the mild steel, this coating, damage of the coating could be possible, because always there are dirts and other things. So, there could be damage of the coating, and there could be the possibility of contamination of the stored water. Now, if we think that let us make the bottom of this section, bottom of this tank with stainless steel in order to have less corrosion, and so that we can have less contamination as well as very small corrosion rate or very low corrosion rate of the bottom, because the bottom part is always exposed to corrosives. So, let us change the bottom part. Let us change the bottom part with stainless steel. This bottom part is made of stainless steel now. This bottom part is made of stainless steel, and this is basically stainless steel clad, and here we have rest of the thing is mild steel, and we see that, and since this is basically a contact between stainless steel with mild steel, so we extend this phenolic coating up to certain distance, and the bottom of this, and here also we extend this phenolic coating just to avoid this galvanic effect at this zone, since this is mild steel is anodic and stainless steel is cathodic as well as noble in the galvanic couple. Now, we think that this will function better, because we have stainless steel at the bottom, and this stainless steel corrosion rate is very small, very low in this mildly corrosive water solution. But the situation is entirely different. After some day, maybe after few months, previously this used to operate for more than 10 years. Now, after few months, this section, the joint section where we have mild steel and stainless steel joint, okay, that section there is a possibility of leakage. There is a possibility of leakage. Why it should happen? And every time we have this situation. Now, the main point is, we can see that whether the situation is due to some corrosive or oxygen, dissolved oxygen level or something, or heavily corrosive action. So, we can do one experiment. We can put mild steel, stainless steel, and in a stainless steel, the same stainless steel, we put water, same water, and then boil it. So, we see the corrosion rate, we do not see much of corrosion rate, okay? It is a very low corrosion rate. The main thing is, since we are boiling it, that time we are basically taking care of oxygen, dissolved oxygen will go out, and there would be very less corrosion effect. Now, why this is happening? Now, this phenolic coating, always there could be some minute pores in the coating, very small pore, let us say very small pore, a very small pore which is there in the coating. This part, let us say a very small pore, or there could be a small crack due to operation. Now, if there is a small pore, water or the corrosive can seep in, and if water seeps in, now we are the solution or the corrosive is seeing mild steel. if it sees mild steel and now the bottom part is exposed to the solution, since there is no phenolic coating at the bottom, and this section is having huge area, and we know that if mild steel and stainless steel, these are clubbed, then mild steel will be active and stainless steel will be noble in the system. So, the mild steel corrosion would happen and stainless steel corrosion would not happen. Now, what would be the rate of mild steel? Since we have a large area then of the cathodic area and a very small area which is exposed to the corrosive, then this situation will prevail there again. So, the rate of corrosion at this zone would be manifold, and gradually this will dissolve and there would be leakage. And this is also happening because we have large exposed cathodic area and a very small anodic area. Now, how would we protect it? The simple protection would be if we can extend this phenolic coating even and cover up the entire stainless steel bottom. See, if we cover up the entire stainless steel bottom, then we do not experience this phenomena of large cathodic area and small anodic area, which is very unfavorable with respect to this galvanic corrosion. So, the protection would be like this. So, there are three examples we have discussed, and in case of unfavorable area ratios, the corrosion rate of the anodic zone would be very high, and then finally, there could be failure in a very short duration. Now, we see that galvanic corrosion is definitely bad and we have to control it, we have to protect system from galvanic corrosion. We can have different mechanisms. Okay. So, what are those mechanisms, or what are the ways we can protect corrosion rate or galvanic corrosion? One is, let us see different ways of corrosion protection or the galvanic corrosion protection. One is choice of metals and alloys. We have to choose metals and alloys for a particular structure in such a fashion that they are very close in the galvanic series, so that we do not have much of potential difference between different metals, and subsequently we do not have much of problem with the galvanic corrosion. Now, second is unfavorable area, that means large cathode and small anode. This part, unfavorable area, that is to be avoided. That is to be avoided. Then third is use of coating. And in the use of coating, if we simply coat the cathodic area, exposing the anode surface, we can have a very good protection. So, coating, use of coating, and always try to cover cathodic area. Even you can expose the anodic area if we can cover the cathodic area. So, if we do not have cathodic area, we do not have the problem of, we do not have the more of cathodic reaction that could have happened on the cathodic surface. Now, fourth is we can have inhibitors which take care of corrosives or some ions. We can have cathodic protection. We can have cathodic protection. Now, Another position where we can experience galvanic corrosion, let us say we have a threaded joint, these plates are, this is basically the threaded joint. Now, we have, this is the, let us say a screw or thread bolt. Now, in that case, most of the cases the bolt material would have higher strength compared to the material which is being fastened. Now, and the bolt material of course, would be a different material compared to the material which is basically threaded, which is fastened. Now, in this case, how to avoid galvanic corrosion, because these two materials, this material and this material would have a different compositions, and there could be a possibility that this material is cathode or this material is anode. If this material is anode, then the problem is much higher. We have seen that steel rivet and copper plate. So, that case, one possibility is we can use some non-metallic sleeve in this zone to avoid galvanic contact. So, if we use non-metallic sleeve, then we cannot have much of contact, electrical contact between the material, between this bolt and the base material, which are basically getting fastened. Now, another thing is, here also we can put a rubber gasket. Rubber gasket we can put. So, this way also we can protect. So, these are some of the protection mechanism or protection ways where we can avoid galvanic corrosion to a great extent. Now, we have been discussing about the problems with galvanic corrosion. Now, galvanic corrosion may be advantageous. Let us see what are the advantages. The one major advantage is, if we do not have galvanic corrosion, then we cannot make dry cell battery. Since we have this galvanic effect, that is what we are going to have the benefit of battery. So, battery, one is cathode, one is anode, and that is what this potential difference between cathode and anode in that particular electrolyte gives rise to the electrical energy or the chemical reaction that is happening, and chemical energy is converting into electrical energy, and that electric energy is basically happening because the galvanic potential difference between the cathode and anode. Second case, as we have seen in case of electrochemical ways of protection, we see that there is a route called, there is one particular route through which we can protect the material, that is cathodic protection. And in cathodic protection, we have two ways. One is sacrificial anode and one is ICCP, which is impressed current corrosion protection or cathodic protection. So, now let us see this one, where we see most why we do galvanization of steel. In case of galvanization, we put a zinc coating, and the zinc acts as anode and steel acts as cathode. Cathodic reaction, which is the oxygen reduction, that happens on the steel surface, and zinc will dissolve, and by the way, and when it dissolves, that time it protects the steel surface. How? Let us say some part is broken. If entirely this is covered, no problem, we have much better way of protection. But if something is disturbed and some part is disturbed or broken, then we have steel surface which is exposed, and on the steel surface we have this reaction. We have this reaction. So, we know that if cathodic reaction happens on a particular metal surface, that part is cathodically protected. Now, and when we have this reaction, then zinc would dissolve and supply electron for this reaction. So, this is my anodic reaction. So, zinc is sacrificing itself and it is protecting the steel surface, and this is giving rise to one particular mechanism for cathodic protection, that is sacrificial anode. Now, if let us say we use tin coating, this is steel and we are using tin coating SN, and also in atmosphere tin is staying above steel in the galvanic series. Now, if there is no damage on the tin surface, this will function better than this, but if there is any damage, now the situation is very different. Now, in this case steel will act as cathode and this part will act as anode, and since we have a large area of the cathode, then this part will be corroded at a very fast rate because of this unfavorable area ratio. So, the tin coating is not advisable and zinc coating is advisable. So, this is one particular advantage of cathodic or galvanic corrosion. Since there is a galvanic couple, and due to this galvanic couple, zinc is corroding and protecting the steel surface. Another particular advantage is cleaning of silverware. Cleaning of silverware. How would we do that? Generally, if you go to some person who makes ornament, what he does, he has one particular bowl, and that bowl is nothing but the aluminum made bowl. Now, in that bowl what he does, the silverware he puts in the solution, and there is a solution which contains baking powder. Now, and he heats it. It is basically a warm water, hot water, and there he puts this silverware, and the silver has a particular problem. Silver becomes dark or black as we use them. This black silver is nothing but the silver sulphide, Ag2S. This looks black. Now, if we have this aluminum bottom and silverware, now in the presence of aluminum, this reaction happens. This reaction happens. Now, you see there is a galvanic contact between this, and this acts as anode and this acts as cathode. So, if this acts anode and this acts cathode, so this will oxidize and this will reduce, and the reduction product is Ag, which deposits back on the silverware. Fine. So, here you see this is reducing and giving rise to silver, or the reduction reaction is happening, that means Ag plus E going to Ag. This reduction reaction is happening, and here aluminum releasing 3 electron going to Al plus 3. So, due to this there is no silver loss, silver again redeposits back, and during this process always there is a foul odor which is just like a rotten egg, okay, because we have sulfuric H2S that evaporates, because this one hydrolyzes and the hydrolyzes product is nothing but H2S, that is what it gives a very foul odor, okay, and this one will hydrolyze it will go to this H2S gas will go up, and then it lead to a foul odor. So, this is the way silverware is cleaned, and during that process we do not have any silver loss. Let us say we scrap it with some scrapper, okay. That time this scrapping business would take care of this particular Ag2S, and we have silver loss, but this method will always recover this oxidized silver, and that oxidized silver will go to silver again due to this reaction. So, this is the cleaning of silverware, and this is taking the advantage of galvanic corrosion.